everyone, my name is Supporter Isaac Berry from Berry Science Lab, and today I'm going to be talking about a fluid flow, specifically a fluid flow with a background potential flow and a little point vortex in the center. So, what does that look like? Well, let's draw it. So, we start with a constant potential flow. It's just ux. Now, what are we going to do here? Well, I'm going to add a point vortex. Now, this point vortex is going to induce a circular flow around it. Let's say it has a strength m. Then, what is the velocity field here going to look like? Well, we're provided a velocity potential function. W of z is equal to m over 2 pi ln z minus uz. What's going on here? Well, essentially, we're using complex numbers as a substitute for coordinates. So here, z is x plus yi, or iy. Now, what happens if we try to find u of z? Well, that's just the negative, usually it would be the negative gradient, but here, since we're dealing with one variable, it's just the negative derivative of w. That's one of the many things that complex coordinates makes easier. So that's just minus m over 2 pi z plus u. Okay, u minus m over 2 pi z. And of course, u is a positive real number. So that's representative of it only acting in the x direction, since it doesn't have a complex coordinate, or it doesn't have an imaginary component, so it doesn't have a y component. So now, what would happen if we tried to make this into, the classic Cartesian coordinates? Well, we can do that. You take u of z is equal to u minus m over 2 pi 1 over z. But what's 1 over a complex number? Well, let's say we have 1 over a plus bi. It's well known that multiplying a complex number by its conjugate, which is a minus bi, will give you a totally real number. So, this should just be the inverse. Why? Well, if you multiply z by this, first this just gives you the modulus squared, and then this cancels it out, making it 1. So that means this is equal to this. That's weird. Okay. So now, u of xy is just, the real coordinate is the x. Yeah, I think it's a little bit chalky in here. Okay, now u is totally real, so its imaginary part is 0. And what's this going to be? Well, the imaginary part of z conjugate is just minus y, since z conjugate is x minus iy. So you get that this is, thank you. This gives you u minus m over 2 pi x over x squared plus y squared, comma, minus m, wait a second, oh, minus m minus y, which means this cancels out and makes it positive, so you get 2 pi x squared plus y squared. Okay, so you get this. Now, what do we do with that? Well, first, let's sketch this, because this is probably pretty interesting. Now, we already know how this is going to look on its own, right? If u is equal to 0, this is just m over 2 pi r minus xy. What does minus xy look like? Well, that's going to be, it's going to get stronger as you move out this way, and it's going to start pointing up like this. So it kind of looks like this. Right? So it all channels towards the origin. After that, it's going to channel either up or down, just like so. So streamlines might look a little something like this. Now, of course, we have the over R modifier, which makes this look a little more like this, and remember it's actually, wait, is it m over 2 pi? Oh, it's r squared. Oops. So that's actually going to make it decrease as you get farther from the origin pretty quickly to 1 over r. So this is already going to be pretty small. This is going to be even smaller. It's overall a pretty quiet field once you leave the origin. Yeah, something like this. Now, imagine adding the potential flow to that. What you're doing is you're adding on a constant doot, 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 doot. So eventually, because this gets weaker away from the origin, it's all going to assimilate into this giant constant field and only differ from it when you're near the origin. So what's it going to look like? Well, something like this. You're going to have, since we're mixing red and green here, I might as well go with brown. Looks like shit. You get something like this, and then bending over even more, and at this time it's pretty much total dominance. Going the same way, same magnitude, same direction over here. It's maybe a little bit off over here. Same direction. It's a little off over here, and it's a little bit off over here. And eventually it's gonna change direction. As you can see, it's kind of a total mess. And since it's going this way, this is actually going to get stronger, but it's once again going to assimilate into that same field once you're far away from the origin. Yeah, I think the picture is starting to become clear. Okay, there we go. So as you can see, it gets fine at the beginning, but it differs at the beginning, but it slowly assimilates into just the soup that is the initial potential flow. All right. So that's a nice sketch of what's actually going on. It's a point vortex disrupting a few things in a mostly uniform potential flow. So now, here's what we're going to do. We are going to find the stagnant point. Now that's actually very easy because all you want to do is make sure the velocity is zero. That's why they call it stagnant. And here you don't even have to convert to Cartesian coordinates. You work with u minus m over 2 pi z is equal to 0. So u is equal to m over 2 pi z. You invert 2 pi z over m is equal to 1 over u. Z is equal to m over 2 pi u. And yep, that's the coordinate. And since m is supposed to be real, u is supposed to be positive real, that implies that z, this stagnant point, lies entirely on the x-axis because it has no imaginary component. So this is our stagnant point. Alright, so, can we see it here? Yeah, you almost can. In the middle of this guy changing directions, there's going to be a stagnant point right around, let me change this back to red. Yeah, there's going to be a stagnant point right around here. The flow is slowing down and changing direction. Okay. So, we have the stagnant point, but what we're going to do now is so much more interesting. We're going to find the streamline of this flow that contains the stagnant point. Looks like this. Now, how do we find that? Well, first we have to find the stream function. The level sets of the stream function, the level curves, are what give us these streamlines. Now, the stream function is pretty simple. This is equal to minus the x component of u, and this is equal to the y component of u. But if you remember, it's a very bad idea to use Cartesian coordinates when you talk about the stream functions of point vortices, since they become undefined at 0, 0. The best way to go about it is using another coordinate system that freaks out at the origin, like polar coordinates. So instead you have UR is equal to, instead you have UR is equal to 1 over R partial psi partial theta, and U theta is equal to minus partial psi partial R. So what are these components? Well, you'll recall that for a point vortex, this component is going to just be m over 2 pi r, and the other component is going to be, well, 0. Wait, is that true? No, that's not true, is it? No, yes, it is. It is. Yeah, okay. But remember that we have a potential flow added to the system. And this potential flow is going to kind of mess with everything, because a potential flow in polar coordinates is not going to be the same tidy regular vector. It's going to be u cosine theta minus u sine theta. So plug that in and you get what? Well, here you multiply both sides by r and get m over 2 pi plus ur cos theta is equal to partial psi partial theta. And here, u sine theta is equal to partial psi partial r after negating both sides. Now you integrate with respect to theta, and you get m over 2 pi theta plus u r sine theta. Yes, the integral of cosine is sine, not negative sine. Just think about what happens when you take the derivative again. But remember that you can't forget the constant function of r that will go away once you take partial derivative with respect to theta. So this is psi. But how do we know what this is? Well, by solving this equation. This will give us u r sine theta plus g of theta. No. Is equal to psi as well. Now we set these equal to each other. And we find g theta and h of r. Now that means that these two are going to cancel out, and g of theta is going to be equal to m over 2 pi theta plus h of r, and the only way this can work is if h of r is equal to 0. So h of r is equal to 0, g of theta is equal to m over 2 pi theta, and psi is equal to u r sine theta plus m over 2 pi theta. What now? Well, we convert back to regular coordinates. Psi is equal to uy plus m over 2 pi arctan y over x. Now all we need to do is set psi is equal to 0. And what do we get then? Minus uy is equal to m over 2 pi arctan y over x. Multiply both sides by 2 pi over m, and you get minus 2 pi u over my is equal to tan inverse y over x. So you get tan of minus 2 pi u over m y is equal to tan, oh sorry, not, please don't. Did it crash? Yeah, I knew it.
Okay, we're gonna come to the movement.
Alright, so I don't have a marker. Great.
Let me find it.
Let me wait. Okay, it's back.
Oh, it's back out here.
Doesn't matter.
Okay. Nothing lost?
No. So, tan is an odd function, so you can just move the minus outside. Invert everything and multiply both sides by y. You get minus, oh, there's a sign here. Okay, so technically the correct version is supposed to be y cotan 2 pi u over my. So just ignore that real quick. So this is the final form for the streamline that contains this point, m over 2 pi u. And this is the streamline that separates all the streamlines that get affected by the point vortex and all the streamlines that don't care about it and go about their day like it was nothing. So that's the difference between this streamline and all of the other ones. This is the separator between the ones that fly away and the ones that get redirected.